Welcome to your first semester of Inorganic Chemistry at Delhi University. Today, we are going to explore one of the most fundamental concepts in all of chemistry, electronegativity. We will learn exactly how atoms compete for electrons and how brilliant scientists like Linus Pauling figured out how to measure this invisible tug of war. Understanding this concept will unlock your ability to predict how molecules behave. To begin, imagine two friends playing a game of tug of war with a shared rope. Even though they share it, the stronger friend pulls the center closer to themselves. In chemistry, atoms do the exact same thing when they share electrons to form a bond. Electronegativity is simply a measure of how strongly an atom pulls those shared electrons toward itself. It is not a standalone energy value like ionization energy, but rather a relative ranking system. It tells us which atom wins the tug of war when two different atoms link together. Now that we understand the concept, let us visualize this tug of war. Here you see a hydrogen atom bonded to a fluorine atom. Because fluorine is much more electronegative, it acts like the stronger friend, pulling the shared electron cloud toward itself. This unequal sharing creates a partial negative charge on the fluorine, denoted by delta minus, and a partial positive charge on the hydrogen, denoted by delta plus. This separation of charge is what gives the bond its polar character. With this visual in mind, how do we actually measure this electron greed? Linus Pauling was the first scientist to create a mathematical scale for it. He noticed a fascinating pattern. When two different atoms form a bond, that bond is almost always stronger than what we would expect if they were sharing electrons perfectly equally. He realized this extra strength comes from the ionic character of the bond, the positive and negative ends attracting each other like magnets. To measure electronegativity, he decided to compare the actual measured bond energy to a theoretical, purely covalent baseline. To find that theoretical baseline, Pauling used this specific formula. Conceptually, if we want to know exactly how strong a perfectly equal 100% covalent bond between atom A and atom B should be, we look at the pure bonds of A with A and B with B. The symbol E sub C represents this expected covalent bond energy. The symbols E sub AA and E sub BB represent the actual, measurable bond dissociation energies of pure diatomic molecules, usually measured in kilojoules per mole. By taking their geometric mean, multiplying them together, and taking the square root, we establish our baseline strength. If the actual bond is stronger than this baseline, the difference is due to electronegativity. Once we have our baseline, we subtract it from the actual measured bond energy to find delta, the extra ionic resonance energy. This brings us to Pauling's final equation. The symbols chi sub A and chi sub B represent the electronegativity values of the two atoms. The vertical bars mean we take the absolute value. The constant 0.102 is a specific conversion factor used when delta is measured in kilojoules per mole. Pauling arbitrarily assigned fluorine a value of 4.0 and calculated all other elements relative to it. Let us see this formula in action with a concrete example. We want to find the electronegativity of chlorine. We are given hydrogen's value as 2.1 and the bond energies for pure hydrogen, pure chlorine, and the hydrogen-chlorine molecule. First, we calculate the expected perfectly covalent bond energy by plugging the pure bond energies into our geometric mean formula. Multiplying 436 by 242 and taking the square root gives us 324.8. Next, we subtract this theoretical baseline from the actual measured bond energy of 432, revealing an extra stabilization energy of 107.2 kilojoules per mole. Continuing with our calculation, we now plug our extra energy value, delta, into Pauling's main equation. We write the difference as chlorine minus hydrogen because we know chlorine is more electronegative, keeping the result positive. Taking the square root of 107.2 and multiplying by a constant 0.102 gives an electronegativity difference of 1.05. Finally, by adding hydrogen's value of 2.1 to this difference, we find that chlorine has a Pauling electronegativity of 3.15. This physically means chlorine is significantly more greedy for electrons than hydrogen. While Pauling's method was brilliant, it relied on bond energies, which are properties of molecules, not isolated atoms. Robert Mulliken took a different, more direct approach. He argued that an atom's electronegativity should be based on its own inherent atomic properties. Specifically, he looked at ionization energy, the effort to remove an electron, and electron affinity, the energy released when gaining one. If an atom holds on to its own electrons tightly and strongly attracts new ones, it must be highly electronegative. Mulliken simply took the average of these two values. This brings us to Mulliken's formula. Conceptually, an atom's overall desire for electrons is just the midpoint between its reluctance to lose one and its eagerness to gain one. The symbol chi sub m represents the Mulliken electronegativity. IE stands for ionization energy and EA stands for electron affinity. Both must be expressed in electron volts for this specific average. Because this gives an absolute energy-based number, scientists later found that dividing the Mulliken value by an empirical constant of 2.8 gives a very close approximation to the familiar relative Pauling scale. Let us apply Mulliken's approach to an atom of fluorine. We are given its ionization energy as 17.4 electron volts and its electron affinity as 3.4 electron volts. First, we add these two values together to get 20.8 and divide by 2 to find the simple average. This gives a Mulliken electronegativity of 10.4. To convert this absolute measure into the relative Pauling scale, we divide by the conversion factor of 2.8. This gives a final estimated value of 3.71, which is very close to Pauling's officially assigned value of 4.0. A third major way to calculate electronegativity was developed by Allred and Rochow. They viewed the problem purely through the lens of electrostatics, the physics of positive and negative charges attracting each other. They argued that electronegativity is simply the actual physical force that the positively charged nucleus exerts on an electron at the outer edge of the atom. By treating the atom like a tiny magnet, they used Coulomb's law to calculate this force, which depends on the effective nuclear charge pulling the electron and the covalent radius, which is the distance to the bond. To calculate this electrostatic pull, we use the Allred-Rochow equation. Conceptually, as the effective nuclear charge increases, the atom pulls harder. As the radius increases, the electrons are further away, so the force drops. The symbol Z sub F represents the effective nuclear charge. The symbol R represents the covalent radius, which must be measured in angstroms. The fraction represents the core electrostatic force from Coulomb's law. Finally, the numbers 0.359 and 0.744 are mathematical adjustment constants, chosen so the final answers line up nicely with Pauling's original scale. Let us calculate the Allred-Rochow electronegativity for a carbon atom. We are given its effective nuclear charge as 3.25 and its covalent radius as 0.77 angstroms. We substitute these values directly into the empirical formula. Following the order of operations, we must first square the radius in the denominator, which gives us 0.5929. Next, we divide the effective nuclear charge by the squared radius. This division gives us 5.48, which represents the raw physical pull of the nucleus on the outer electrons. Continuing our calculation, we must now scale this raw physical value to match the traditional chemical scale. We multiply our force factor of 5.48 by the scaling constant 0.359, which yields 1.967. Finally, we add the offset constant of 0.744. This gives a final calculated electronegativity of approximately 2.71. This matches closely with carbon's accepted Pauling value of 2.55, confirming that carbon has a moderate but significant pull on shared electrons in a bond. Now that we have calculated these values, why do we care so much about electronegativity? It is arguably the most powerful predictive tool in all of chemistry. By simply looking at the difference in electronegativity between two atoms, we can predict exactly what kind of bond they will form. If the difference is zero or very small, they share electrons equally, forming a non-polar covalent bond. If the difference is moderate, they form a polar covalent bond, creating molecules with positive and negative ends. If the difference is massive, one atom completely rips the electron away, forming an ionic bond. To summarize, electronegativity is the ultimate measure of an atom's ability to attract shared electrons in a chemical bond. We explored three ways to calculate it. Pauling used bond energies, Mulliken used atomic ionization and affinity energies, and Allred-Rojo used the electrostatic pull of the nucleus. Regardless of the mathematical scale used, the core concept remains exactly the same. It serves as your fundamental guide for predicting bond types, molecular polarity, and how different chemicals will interact in the real world. You now have the foundation to understand chemical bonding.